Hi, my name is Sayoung Kim, and today I will present our work titled Uncertainty-Guided Compositional Alignment with Part 2 Whole Semantic Representativeness in Vision Language Model. This is joint work with Jiha Jang, Junghoon James Kim, and Se-young Chun from Seoul National University. Let me start with our motivation. Given a whole scene image, we can crop several box-level part images from it. For example, in this street scene, we may have boxes corresponding to the streets, people, cars, and traffic sign. However, an important question is, how well does each box image represent the whole scene? Not all parts are equally informative. Our key observation is that part-whole alignment should not treat all parts equally. This motivates our main idea. We need uncertainty-aware part-whole alignment. Today, I'll first introduce the background and motivations, then explain our method, and finally show experimental results. The central idea of our work is simple. We model part-to-whole representativeness using uncertainty in hyperbolic space. But what exactly is hyperbolic space? Hyperbolic space is well suited for representing hierarchical and tree-like structures. Unlike Euclidean space, the volume of a ball in hyperbolic space grows exponentially with its radius. This makes hyperbolic space very effective for embedding hierarchical relationships, such as abstract to specific or whole to part structures. Here, we visualize hyperbolic space using semicircular geodesic arcs. These arcs help illustrate how hierarchy and entailments are represented in the projected hyperbolic space. In hyperbolic space, uncertainty is represented by the distance from the origin. Features closer to the origins are generally more abstract and uncertain, while features farther from the origins are more specific and less uncertain. This interpretation has been used in prior hyperbolic representation learning, and it is especially useful for visual understanding because images and their parts naturally form hierarchical structures. One related work is Meru, which extends hyperbolic hierarchy to the multimodal setting. Meru treats text as more abstract and images more specific. Based on this assumption, it defines an entailment relationship where the text entails the corresponding image. So the text representation should entail the image representation in hyperbolic space. Another closely related work is Hyperclip. Hyperclip goes beyond whole image text alignment and jointly consider part and whole representations. It also models part-to-whole entailments, where the whole scene entails its parts. This is important because real-world scenes are compositional. A scene contains multiple objects and parts, and understanding this relationship is crucial for compositional vision language learning. Now let's move on to our method. Existing methods do not explicitly consider that different parts can have different level of representativeness. In other words, they do not fully address the multi-object case, where some parts are more informative to the whole scene than others. That's why we need uncertainty-aware part-whole alignment in hyperbolic space. Consider a scene of a person snorkeling underwater. In a multi-object scene, not every part contributes equally to the meaning of the whole scene. Some parts are highly representative, while others are relatively peripheral. To model this, we define representativeness using hyperbolic uncertainty. Specifically, we use hyperbolic radius, or the distance from the origin, as an uncertain measure. The intuition is, if a part is more representative of the whole, its uncertainty should be lower. If a part is less representative, its uncertainty should be higher. This lets the model adaptively control how strongly each part should be aligned with the whole. Our method consists of two main components, uncertainty-aware contrastive loss and entailment loss. First, we introduce as uncertainty-guided global-local contrastive loss. Let's first look at the prior contrastive learning setup. In existing hyperbolic visual language model, there are two types of alignment. The first one is global alignment, which aligns the whole image and the whole text. The second is global local alignment, which aligns box-level part representations with the whole scene representation. However, this alignment is usually applied uniformly. That means every part is encouraged to align with the whole in a similar way. To solve this, we propose an uncertainty-guided global local contrastive laws. The key idea is to adaptively set the temperature based on uncertainty. This is over a figure of the uncertainty-guided global local contrastive laws. For the part with high uncertainty, we use higher temperature. This procedure loses alignment because the model should not force the uncertain or weakly representative part to be too close to the whole scene. For a part with low uncertainty, we use lower temperature. This procedure stronger alignment because the representative part should be closely aligned with the whole scene. In other words, uncertainty controls the strengths of the global local alignment. This allows the model to distinguish between central representative parts and less informative parts rather than treating all boxes equally. Next, let's discuss the entailment laws, the piecewise continuous entailment laws, and uncertainty calibration laws. In hyperbolic space, entailment is often modeled using an entailment cone. Given an embedding P, the cone defines a region of embeddings that can be entailed by P. First, the piecewise continuous entailment cone. The prior hinge-based entailment laws penalize a point when it falls outside the cone. This is useful for modeling hierarchical relationship, but it has a limitation. Once a point is inside the entailment cone, the loss becomes zero. As a result, the model no longer receives useful gradients inside the cone. To address this issue, we propose a piecewise continuous entailment laws. This can be understood as a regularized relaxation of the original hinge-based entailment laws. Instead of giving exactly zero gradients inside the entailment cone, our laws allow small gradients even when the entailment condition is already satisfied. This encourages the model to continue refining the structures of the embedding space. As a result, the model can learn more stable and fine-grained hierarchical relationship. We also introduce an uncertainty calibration loss. The goal of this law is to prevent embedding collapse in hyperbolic space and to clearly separate global and local representation through calibrated uncertainty. If the entailment loss is large, the model is encouraged to increase the uncertainty of the corresponding representation. At the same time, entropy minimization prevents all uncertainty values from collapse to one side. This calibration is important because uncertainty should be meaningful. It should not simply become uniformly high or uniformly low. Instead, uncertainty should reflect how representative each part is with respect to the whole scene. Now, let's look at the experimental results. First, we evaluate zero-shot image classification. Our method achieved competitive or improved performance compared to the previous hyperbolic vision language model. These results show that introducing uncertainty-guided part-whole alignment does not hurt global image-level recognition. Next, we evaluate zero-shot retrieval and hierarchical metrics. Retrieval measure how well image and text representations are aligned across modalities. Hierarchical metrics further evaluate whether the learned space capture meaningful hierarchical relationship. Our model improves this metric. We suggest that uncertainty-guided alignments help the model organize representation more effectively in hyperbolic space. This is important because our goal is not only to improve classification accuracy, but also to build better structured multimodal embedding space. We also evaluate zero-shot box-level image classification. This task is directly related to part-level understanding. Our method shows strong performance on the task, which support our main hypothesis. Modeling part-to-whole representativeness helps the model better understand local visual components. We further evaluate our method on multi-level classification and zero-shot segmentation. These tasks require understanding multiple objects or regions within the scene. Therefore, they are more compositional than standard single-level classification. The result shows that our method is effective not only for global image text alignment, but also for dense and multi-object visual understanding. This slide visualizes part images sorted by UNCHA's calibrated uncertainty. We can observe that the model assigns differently uncertainty value to different parts. These visualizations support our main claim. The model learns to use hyperbolic space more effectively by calibrating uncertainty according to part-to-whole representativeness. Lastly, we show qualitative results for compositional scene understanding. Each row shows an attention map for a different query, and each column compares different vision language models. These examples are challenging because they contain multiple objects. In the dining room example, baseline method often active broader regions such as the entire furniture area. In contrast, UNCHA produces more focused attention on the queried objects. Similarly, in the outdoor example, the model needs to distinguish between bicycle and person. UNCHA gives more localized and less noisy activations compared to the baseline. These results suggest that our uncertainty-guided partial alignment helps the model better handle multiple objects compositional scene. This is the end of the presentation. Thank you for listening.